Good morning, guys. Welcome to Friday. Yay, Friday. Um, so we have some tough stuff to talk about today. A couple of things I want to go just reminders before we get started. So the first exam is next Wednesday. So we will have class today. This is the last material that will be on that test. Monday, we will talk about a different subject, talkways solutions, but that will not be on the test. That is to give you some additional time to get ready for taking the test, make sure you've got everything straightened down and narrowed up and all of that lovely stuff. The Alex homework will be due on Monday, so 2 days before the test. That is typically how things are done. So try not to wait until the last minute to make sure that you've done your Alex. Between the Alex practice and what is on D2L for this, we should be fairly well prepped for the test. So things that you may want to look at in terms of getting prepared for that, in case you haven't seen them yet. If we're looking in exam 1 materials, you'll see that there's an exam 1 practice. There is an answer key that goes with that. I will be happy to answer any questions that you have about that anytime before the test, including the day of the test. So I will be in WebEx that morning, the entire time you're supposed to be taking the test. Again, the test is supposed to start at 8, it's supposed to end at 10. It is a 2-hour enforced time limit. As long as you start it before 10, it's not a huge deal. If you have any scheduling issues with that, let me know. We can make other arrangements, but we need to make sure that that gets done before the test is supposed to happen and not after the fact. So unless something weird happens and you end up not being able to take it at the time, then there are things that can be done about that. Like I said, the answers are here for that practice. I am a very big proponent that my questions on tests should come from the material that you've seen. So you may see some of these questions exactly as they're written on the test. You may see variations of these questions on the test. So this should be a good preparation for you in terms of what you would expect. My expectation also is that you have the exam handouts, and those can be found in the course documents. You'll see there is an exam handouts here. The expectation is that you have printed these so that you can have them with you. The Respondus lockdown browser should be shown these things. The only reason that I want to see them is to see, have you written anything on them, because you're not supposed to. But I understand that that's how these things go. So one of the things that I wanted to show you today, so like I said, Avogadro's number is on here, so make sure that you're aware that that number is there. It's not labeled that way, but it is present. A couple of other things. We'll be talking in great detail about this diagram today, parts of this diagram today. So remember that this is available to you as well. Not all of this material is relevant to you guys, and it doesn't always occur in an order that makes sense. It's in the order that it fit on the paper. So that's how I did that. But there are things like the common names that are useful to you guys, and then there's a bunch of stuff that around it that is not necessarily things that you need to be worried about. Okay, I use this for both 110 and 111, so there's stuff in here that doesn't apply to you, and not all of it applies yet. So there's that as well. So you will be using that set of exam handouts for all of the exams. Again, my preference is that you get used to it before the test, because then you know where things are. So, if it's like, oh, I need Avogadro's number, I know where that is, I can go find it. But it's harder to do that if you haven't really taken a look at what you're being offered during that exam. Okay. One of the other things that I will tell you is that there sometimes are questions on the test that are related to each other. This is not something that's always done intentionally, but they may be two versions of the same kind of thing. So you may find an answer to a question somewhere else on the test. So just make sure that you're checking all of your resources available for that. I do have a couple of things that I like to point out as test taking things. I will load those to D2L, and I'm actually going to put those in with the course documents. So there's some test taking stuff, there's some problem solving stuff. There's, if you've looked at the lab, there's a scientific method thing that will go into the course documents as well. So that's everything I have related to test. So Monday's lecture, again, will be new material. and then review for the test if you want it. And if you have any questions for me anytime between then and when you take the test, let me know. I will do my best to have that test graded on Wednesday, but I have something I have to do, so I may or may not actually make that. So you will definitely have it back by a week from Wednesday, but you should have it before that. Okay. So any questions about that before we get started on other stuff? All right. I'm going to go ahead and pull this up. And we're going to be talking about stoichiometry and limiting reactions today. That's our general topic that we're going to be talking about. You'll notice that I have three things: stoichiometry, limiting reagents, and yields. And they're very big type because that's all we're really going to be talking about. And that sounds like a lot of, not a lot of stuff, but stoichiometry is a really big topic. So we need to spend some time on it. So there is that. But before we do that, we need a little review of what we talked about the last time. So what we did last time was to talk about how we balance equations. So I have some questions here that I wanted you to take a look at. Hopefully you've had a chance to look at those. And we're going to go through the balancing of these reactions. So I look at my first one right here. I have an Mg, I have an O, I have an H, and I have a Cl. I see that I have one Mg on my reactant side, and I have one Mg on my product side. I have three H's on my reactant side. I have two oxygens on my reactant side, and I have one chlorine on my reactant side. On my product side, I have two chlorines, I have two hydrogens, and one oxygen. So the first thing that I see that's an issue, my Cl2. My Cl, there are two of them on the product side, one on my reactant, so I'm going to fix that over here. That'll then give me two of those, and that changes my total for H to 4. And I have 4 of those, so my H's are messed up. That's okay, because my O's are messed up too. So I'll change this to a 2, and that of course changes my hydrogen to 4. And I am now balanced. Yay, that was awesome. Sometimes it's easy, sometimes it's not. So let's take a look at our next one. Got an Fe, a Cl, an N, an O, and an H. I have one Fe on my reactant side. I have 3 Cls. I have one N, one O, and 5 H. On my product side, I have one Fe. I have 3 oxygens, 3 hydrogens, 1 nitrogen. Oh, wait. 3 and 7 hydrogens. And 1 Cl. So Fe's are okay. I'm going to go ahead and try and fix my problem with my chlorines. So multiply this by 3. When I do that, that means I have 3 there. I've now changed the number of nitrogens that I have. And I've changed the number of hydrogens total that I have. So I have 3 from here. And 3 times 4 is 12. That's 15 hydrogens there. Since I messed up my nitrogen, now I'm going to have to multiply this by 3. And so now my nitrogens are fixed. That also means that I've changed the number of oxygens. So now I have 3 of those. And 3 times 5 is 15 hydrogens. Yay! I love it when I fix one thing and it fixes everything else too. Makes my life a lot easier. So now we have our C2H6 solid plus O2 gas goes to H2O liquid plus CO2. Okay. I again have carbon, hydrogen, and oxygen. Those are the things that I'm looking at. I see 2 carbons on my reactant side, 6 hydrogens on my reactant side, and 2 oxygens on my reactant side. On my product side, I see 2 hydrogens, 3 oxygens, and 1 carbon. So I need to fix my carbon problems. I'll fix my carbon problem first. That changes my number of oxygens that I have. So now I have 4 or 5 of them. And looking at my H's, I need to fix that issue as well. So I have 6 over here. I'll multiply this one by 3. That will take care of that. And of course, when I do that, that changes the number of oxygens that I have again. So now I have 4 plus the 3 is the 7. And I have 2 over here. So there are 2 ways that I can handle this. One, the way that I like to do it, is 7 over 2, because that'll give me exactly the 7 that I need. but that's not always comfortable for people. And if that's not comfortable for you, that's perfectly okay. We would then multiply all of this by 2. That would then leave me with a 7 there. This would then be a 3 here and a 4 here. And that way they're all whole numbers as opposed to fractions. Again, I do not care which way you do this. It matters for lots of things, but none of them are here and present at this point. So I don't care as long as we have the same number on both sides. Okay. All right. Let's talk about KMnO4 plus HCl goes to KCl plus MnCl2 plus H2O plus Cl2. Right. Okay. So there's a K, there's an Mn, there's an oxygen, hydrogen, and chlorine. On my reactant side, I see 1 potassium, 1 manganese, 4 oxygen, 1 hydrogen, and 1 chlorine. On my product side, I also see 1 potassium, I see 1 manganese, I see 1 oxygen, I see 2 hydrogens at the moment, and 1, 2, 3, 4, 5 chlorines. Right. Okay. So chlorine is the biggest issue, but it's also really complicated because it occurs in a bunch of different places. So I'm going to hold off on trying to fix that. The other thing that I see when I look at this is that I have this Cl2 that's out here. And so if I end up with issues because of balancing everything else, I can usually fix it with that the Cl2 out there by itself. So I'm going to try and fix everything else first. Now, right now, K and Mn are both fine. Oxygen is not, hydrogen is not. So I'm going to try and fix my oxygen first. I'm going to put 4 oxygens out here. That means I now have 4 oxygens there. I have then changed the number of hydrogens that are present here. So I now have 8 instead of 2. And that means I'm going to need to fix something over here. So I can multiply that by 8. And that gives me the 8 that I'm looking for there. I now have a total of 8 chlorines over here. And okay, fine, how am I going to deal with that? Well, this is where things get really fun and we start going, okay, how do I make this work? So if I have 8 on this side and 5 on this side, I can change things by changing the numbers that I have. Now, given that I have 8 over here, so this is an odd, there's 1 by itself. I look at this and I say, all right, what's the easiest way that I'm going to be able to do this? And in my head, for whatever reason, it makes sense to me to multiply things by 2. And there is a reason that I'm doing that, and I don't know how to explain it very well. I struggle to do that. So one of the ways that we need to be able to deal with this is to play around and see what works and what doesn't. So if I multiply this by 2, that gives me 2 Ks. That also gives me 2 Mns, and then that gives me 8 oxygens. I then would have to fix things on the other side, so I have 2 there, so my Ks are okay. That changes my chlorine, so I have 2 chlorines from there, 4 from there, and 6 total that I end up with there. So now I at least have an even number. That makes me happy. And that's why I decided to do it, because I wanted an even number on both sides. Doesn't necessarily mean that it will stay that way, but that's why I initially made the choice. Now that I've done that, I need to fix this guy right here, because I need to have 2 MNs, and that means that I now have 2 CLs, 4 CLs, 6, 4 plus 2 is 6, 8 CLs. Oh, look, 8 CLs. That means that everybody is now happy. I love it when that happens. Okay, so that's what I did with that. Okay, questions about what I did or why I did it? Again, I don't have a really great explanation for why I thought that that was the best place to start. I just know that that makes sense in my head, and I apologize. There is a lot of back and forth that goes with a lot of these things until we get good at these. And I will also tell you that I won't expect you to balance something this ugly on a test. So practicing with it makes it easier to do the easier things. So Questions about that? Okay. Let's talk about our C3H8 plus O2 going to CO2 plus H2O. Again, different combustion reaction. Again, in our combustion, we're going to have carbon, hydrogen, oxygen. I currently have 3 carbons on my reactant side, 8 hydrogens on my reactant side, and 2 oxygens on my reactant side. On my product side, I have 1 carbon. I currently have 3 oxygens and 2 hydrogens. Okay, fine. Let's fix the carbon first. So we'll multiply that by 3. That'll change that. And that gives me 6, 7 oxygens that I have there. I don't necessarily want that. I need to have an even number of oxygens. So I'm going to go ahead and multiply this by 2. If I do that, then I have 6, 8 oxygens. And then that changes the number of hydrogens that I have on that side, which is then 4 that I have there. So not great yet. So let's change this. Rather than 4 or 2 there, let's go 4 here. And if we change that to 4, then that gives me the 8 that I'm looking for with the hydrogen. I now have 4 and 10 oxygens, which I can fix with having 5O2. So that takes care of my oxygen. Sweet. I love it when that happens. Okay. When we look at our last one, our Al plus Fe2O3 goes to Fe plus Al2O3. My oxygen, so I have an Al, I have an Fe, and I have an O. If I look at my Al, I have 1 Al on my reactant side, 2 Fe, and 3 O. On my product side, I have 1 Fe, 2 Al, and 3 O. So it's the Al and the Fe that I need to fix. If I multiply that one by 2 and that one by 2, then I fix both of those issues because the number of oxygens were the same anyway. So there we go. So, questions on any of our balance? Cool. All right. When we talk about our nuclear stuff, what is the formula of an alpha particle? Well, okay. I know that an alpha particle is a 4,2He. I can also write that as a 4,2 alpha. And I know that because I have looked at this picture enough to remember that that is the case. But this is the reference that I would use and the thing that I checked to make sure that I know all of these things are correct, right? And yes, that's the slide that I presented this time. It's the formula of a gamma particle. Gamma is this guy. He has technically a 0 and a 0 on him. He doesn't change anything. He's just energy. So that is my gamma right there. This one does not explicitly show the 0 and the 0, but it's a very just energy that we're looking at. So it doesn't change it. Symbol for our neutron. Neutron is a 10N. Okay. Another name for a beta particle is an electron. And so that's a 0, -1e, or a 0, -1 beta is the 2 ways that I can write that. Now, it didn't ask me that, but I'm writing it down anyway. Write the nuclear equation showing the radioactive decay of polonium-218 if the decay produces an alpha particle. Okay, polonium-218. So 218 is my mass number. PO is the symbol. PO on my periodic table. I have one somewhere. Is right here. He's 84. So I'll put my 84 right there. That's going to give me something and an alpha particle. So 42He. So I know that I have to have the 218 is equal to something plus 4. So 218 minus 4 is equal to 214. So my mass number will be 214 on my product side. And my 84 has to be equal to something plus 2. So if I take 84 minus 2, that gives me 82. So that goes there. Now, when I look at my periodic table again, to see what my 82 is, that's PB, that's lead. So I can put that symbol for PB, and then I'm done. And again, that's what I'm looking for. When I do these nuclear ones, as long as I can identify the nuclear particle that I need to deal with, then I should be able to figure out by inspection what everything else is. Okay? So questions about any of our nuclear stuff?
Not about. Can you hear me?
Yes.
Okay. Not about the nuclear stuff. I was having some issues with my mic when you asked if we had any
Oh,
questions about the stoichiometry.
yes.
Um, the last problem we did, I'm not sure if I'm just not remembering properly or something. Um, there was S's there, and I wasn't quite sure. Like it's ALS, so on and so forth. But whenever
Okay.
you did the stoichiometry, all I'm seeing is the LE, AL, FE, and O. And I just
Correct.
don't know if I forgot what those were or something else.
So this indicates the phase that this is in. So aluminum solid, Fe2O3 solid, Fe solid, and Al2O3 solid. Some of them have them, some of them don't. It is not required that they be there for this, so I don't always include them. It's something that needs to be there when you get to 111, but it doesn't necessarily need to be there at this point. So sometimes they get written, sometimes they don't, and it's not
All right.
important that I have it. So.
All right, thank you.
Yes, absolutely. Anything else?
Um,
Go
if
ahead.
if I was to say, um,
Yes.
I think it was the um, not the isotope. It was when you were going from plutonium to lead, I believe.
Yes.
Um, we're at the nuclear equation showing the radioactive decay. Polonium two 218. If the decay produces an alpha particle. Um,
Correct.
how this is probably just something I've missed, especially considering its review. I think I might have actually slept through class yesterday. I'm not quite sure. Um,
No.
I know, oh no, but I just can't remember class at all yesterday. Um, how do you get that? I guess is the question I'm asking. Like, how do you know to go from 218 to 214?
Okay. So the way that it works with the nuclear stuff is I know that it says polonium 218. That 218 is the mass number. That's what that the thing after is listed as. And so that mass number is what goes up here.
Yeah.
So I know that the 218 goes at the top. I know that it's a PO, and I know that PO on the periodic table, if I find him again, is 84. So that's the number down at the bottom. That's that part. As far as what else happens, it says if the decay produces an alpha particle. So I know that one of my products is an alpha particle, which is that 42He. Now, when I do the balancing on these, the mass numbers, the stuff up at the top, has to equal on both sides. So I know that my 218 has to be equal to something plus 4. And my 84 has to be equal to something plus 2. Hence why I took the 218 minus the 4 to figure out what that last thing was.
Gotcha. Okay, yeah, that makes sense.
Yes.
I guess the last thing I have, and I'm gonna go back over the previous lecture, just to be safe on this. But how do you know that that looks like helium that you're getting
That
out of
is
the product?
correct. Yes. So it is a helium nucleus, and there are a couple of elementary particles that we're looking at. So an alpha particle is a helium nucleus. It's a 42He, also listed as a 42 alpha.
Oh, so an alpha particle will always be helium.
That's correct. Yes.
Gotcha. Okay, that answers my question. Thank you so much.
You're sure. No problem. Anything else?
Not right now.
Okay. Anybody else got anything? Okay. So stoichiometry, for those of us who didn't like balancing equations, guess what? We're still doing it. It's kind of one of those things. So stoichiometry is this big, huge word that we use to talk about the coefficients that go out in the front of the reactions. Okay, that's the first part of this. And then how do we get from calculations of what is the mass that I have here to how much product I can make? Or if I have this mass of this material that I start with, how much of this other starting material do I need to have to do this? From a practical standpoint, as a chemist, if I have something that's really, really expensive that I need to work with, and I need to react it with something else, I need to make sure that I have enough of that other thing to not waste whatever it is that's really expensive. So we need to make sure that we have enough of what we're looking for. And so we can do these calculations to see how much do I need to make sure that this happens. Another thing that we'll talk about is making sure that we actually produce the amount that we need in the end, which is a two-step process, because one, I need to know how much I need to produce, but two, I also have to be able to look at how effective is that reaction, because much as I would love to say that reactions go exactly the way they're supposed to, they never do. So even though I should produce a certain amount, I hardly ever do that. And one of the most efficient processes that we have is actually only 28 to 30% efficient. So we need to be able to take that into account as well, okay? But of course, for us to do that, we have to be able to look at all of the relationships that exist within this balanced equation. So the only way to determine how much of a second reactant or a product we get, if we know how much of one thing we start with, is by using that molar ratio. So for instance, if we talk about the reaction between hydrogen and oxygen to give me H2O, I know that I need 2 hydrogens and 1 oxygen to make 2 H2O, all right? So I know the ratio of H2 to O2 is 2 to 1, and I know the ratio of O2 to H2O is 1 to 2, okay? So there are a couple of things that means to you. One, you have to have a balanced equation before you do any of these calculations. That molar ratio is incredibly important. And two, that molar ratio is going to be part of all the calculations that we do. So you'll see me write it out. Now, sometimes we don't need it, but I would rather write it and not need it than need it and not write it. So I tend to do things in a very systematic way so I don't forget stuff. All right, so that's what we're looking at. Now, I will probably ask you, what is the ratio for things on the test? Because it's an easy way for me to check and see that you could balance something correctly. Okay, so that's a way for us to do that. Right. So you may get asked, what's the ratio of this to this? And you would report it in this way. It will say that on the test. Because yes, there is one of those on the test. All right, so we have a calculation map here. So for now, we're going to ignore the volumes that are written here. Those will come later. And this is a simplified version of what you'll see in the exam handouts. So on the exam handouts, you'll see that there's this image here. And we talk about some of the things that are here. We can go from the number of particles of A using Avogadro's number to get to the number of moles of whatever we're talking about. And I can go from moles to get to grams, or I can go from grams to get to moles. We've talked about those calculations. Today, we're going to be talking about how to go from mass of one thing, moles of that thing, to moles of something else. So we're going to be building on this image that we're doing here. As the semester continues, we will look at all the different ways that we can use these different pathways to get from one to another. So it is possible for us to do that. As we go, we'll continue to build. So this is just a simplified version of that to try and help you understand that, okay, if I have a mass and I know the molar mass, I can get to moles. We've done that. If I know the number of moles, I can get to the number of particles. We've done that. I can go from particles to moles and from moles to mass. We've done that too. Now we're going to talk about how do we get from moles of this thing to moles of something else. And of course, that becomes important because if this thing that I'm talking about right here is H2, and this thing over here is O2, then the ratio between them is not 1 to 1. So we need to take that into account when we do those calculations. So of course, there are 2 H2s for 1 O2. I know that there are 2 H2Os, or H2s and 2 H2Os, so that's a 1-to-1 relationship. That makes things a lot easier for me. But I can also start with an O2 over here and look at how much H2 do I need. So if I'm starting with O2, how much H2 do I require to react with that? Or I could start with O2 over here and how much H2O do I need? Would I get from that? We can also start with the H2O, okay, and go, okay, how much O2 do I need to make that? How much H2 do I need to make that? Okay, so these are the things that we can be talking about, all right? So that's where we're going to be going. And these are the calculations that we're going to do. Now, a reminder before we get into this, there are things that are always diatomic. And we talked about this before. I talked about the 7 that exists on the table: nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And then there's the hydrogen. So we love mnemonics. So have no fear of ice cold beer. That's my mnemonic for how I remember the things that need to be diatomic. Okay? So this is just another way that I can remember that that's important. Because again, if I'm trying to balance an equation and I don't have H2 written as H2, I have it written as H, that balancing is going to be very different. So that brings back, we need to make sure that the formulas we've written down are right before we start that balance. And that those formulas have to do with the charges that exist on the cations and the anions, if we're talking about an ionic compound, or the correct number, the correct ratio from our nonmetal to nonmetal bonds. So if I'm talking about NO2, that's different than N2O4. So we need to make sure that we've got those formulas written correctly when we do them. And of course, that becomes an issue because we often give you the words and not the formulas to start this. But if you get the formulas, it's a little bit easier. One other thing that I have to tell you, and I cannot emphasize this enough, you don't always end up with a balanced equation that's given to you. Sometimes it's a skeleton of an equation, so you need to make sure that it is actually balanced before you use it. Because if it's not balanced correctly, then everything that comes after that fact will be wrong. Now, sometimes that's done intentionally to make sure that you've checked for it. So while it seems mean, it's meant to make sure that you guys are paying attention to what you're doing. Because sometimes you get just a skeleton. You may get, hey, I need you to do this reaction. Some guy in sales has brought you a reaction because he wants to sell this product, and he didn't know that it wasn't balanced. So how can he fix it for you? So you, as the chemist, if you were the one working in there, would need to know that that needs to be fixed and it needs to be checked. Okay, so these things do occur in real life situations. So we need to make sure that we've taken care of that. Okay. The other thing is, it's always good to put a second set of eyes on something. Even though somebody's balanced it, they may have been staring at it far too long and just don't see where they made a mistake. So second set of eyes is always good. And when you're working in a laboratory, we typically have 2 sets of eyes that do anything. That's a requirement for what we do. You may have seen, if you were looking at the notebook example that I gave, that we have to do a countersign on that. And that means that you have to have someone else in the lab check your work for everything that you do. So it's just one of those things. Now, stoichiometry calculations. Industrial ammonia is produced from reacting hydrogen and nitrogen. If I have 16 grams of hydrogen, how much ammonia can I make? Okay. Now, the first thing I'm going to tell you is I have to assume that there's enough nitrogen to do this. Okay, we'll talk about what that means later. But right now, we're going to sort of ignore how much nitrogen there is. So the first thing I need is to write and balance an equation. H exists as H2, N exists as N2. So I've got my H2, I've got my N2, and then I'm going to be making ammonia, which from my common names I know is NH3. So I know I'm going to have to multiply this by 2 because I have 2 nitrogens on the reactant side. And of course, that means that I now have 6 hydrogens on my product side. So I'm going to have to multiply that by 3. So that gives me that ratio that I was talking about that we need to know for this. Okay. So, and that's what you see written here. It's just, I wanted to make sure that I showed you what I was doing. So convert the mass to moles. When in doubt, convert to moles. Always, always, always convert to moles. Do you always need to? No, but if you do, you always get points for it. So there is that. So I have my 16 grams of H2. I divide that by the molecular weight of the H2, which is 2.02. For this one, I used the 1.01 grams of H2. And then it gives me 7.92 moles of H2. That's 3 sig figs because 16 has 3 sig figs. Okay, so now I know how many moles of H2 I have made. 7.92. Okay, awesome. What can I do with that? Well, once I get to moles of this thing, the H2, I can go from moles of H2 to moles of NH3. So I went from grams of H2 to moles of H2. And now I can go from moles of H2 to moles of NH3. Well, that's awesome. So I do that by using that molar ratio from the balanced equation. So 7.92 moles of H2, 3 moles of H2 are required to make 2 moles of NH3. So I divide by the 3 and multiply by the 2, and I just, this ratio that I set up here is exactly what the balanced equation says. That's how I do it. I put the moles of H2 on the bottom, I put the moles of NH3 on the top, and then I put in whatever number was in my balanced equation. That gives me 5.28 moles of NH3. And again, 3 sig figs based on the 16 in the original calculation. I can then convert from moles of NH3 to grams of NH3. So I can go to grams of NH3. And I do that by using the molecular weight of the NH3. I multiply, in this case, by the molecular weight of NH3. So 5.28 moles of NH3, and multiply by 17.04 grams of NH3 per mole. That gives me 90 grams of NH3. Okay. Now, me doing this, would I have written this as multiple steps? No. Can you? Absolutely, you can. If you want to do it that way, that's fine. One reason that I don't write it that way is because I want to remember that I don't want to use those rounded numbers when I do these calculations. So even though I'm reporting a rounded number right here, and I'm reporting a rounded number right here, I want to use whatever my calculator gave me as I continue to do this. So that's why I do this in this fashion. So that's 16 grams divided by the 2.02 times 2 divided by 3 times 17.04. Now, it doesn't matter if I do the multiplication or the division first, or if I do it 16 divided by 2.02 times 2 divided by 3, doesn't matter, because it's multiplication division, so it doesn't matter the order of operation on that. But that gives me that 90 grams of NH3, and it's 90.0, again, 3 sig figs. My steps that I took to do this, I wrote and balanced my equation, and then I converted grams to moles to grams. Okay. Now, do I always need to do that entire thing? No, not necessarily. There are times, and some of the practice that you'll see asks you just to go from moles to moles. Okay. Sometimes we ask you to go from grams of this thing to moles of something else. So there are parts of these calculations that you may get asked to do. All right, that's perfectly okay. As long as we know that the process is grams to moles to grams, we should be able to truncate that if we want or need to. Okay. So any questions so far? All right. Example calculations. Oh boy, we have lots of examples. Sulfuric acid reacts with sodium hydroxide to produce sodium sulfate and water. If 500.0 grams of sulfuric acid is used, how much sodium hydroxide is required? Right. Okay, now I'm going to start down at the bottom because that gives me more space. I'm going to move this out a little bit so I have a little more space than that. So sulfuric acid is H2SO4. Do you need to know that? Not necessarily, no. There is in your exam handouts a list of strong acids and bases. That list is on, what page is this? All right, I'm looking at my handouts, but I can't see the page numbers. So that is page 6 on the exam handouts. So it says sulfuric acid is H2SO4. Okay. So you, again, use what's available to you. H2SO4 is sulfuric acid. Reacts with sodium hydroxide. Sodium is an Na. He's an alkaline metal, so he's in that first. So he's right here. So he's going to lose 1 electron to become an Na+. If he's an Na+ and the hydroxide is an OH-, then that just becomes NaOH, because they're both, it's a +1 and a -1, so it's a 1-to-1 ratio there. Okay, awesome. That's going to give me a sodium sulfate. So again, sodium is Na+, and sulfate, if I look at this, so there are 2 ways that I can know this. SO4 is 2-. I know that that is true because on my exam handouts, in the list of polyatomic ions, this guy right here, I can see that sulfate is SO4 minus. So I know he's a -2 charge. The other thing is that I can tell from looking at this, because H is always +1, that if there are two of them, then it has to be a -2 charge. So if it's an SO4 minus, in order for that to balance, that has to be an Na2SO4. So that's my sodium sulfate. And it makes water, H2O. Now, cool, that's awesome. Now that's an acid-base reaction. So I make a salt and water. The salt made is this. It's called the salt because it's an ionic compound. So there you go. So that's what we have there. That's my balanced equation. All right, awesome. What else do I know about this? I know that I have 500.0 grams of H2SO4 that I'm working with, and I want to know how much sodium hydroxide is required. So I put that as a question mark right there, because that's what I'm looking for. Now, in order for me to answer this question, I know that I'm going to need a mass for H2SO4, because I have to get to moles, right? So I need the molecular weight of H2SO4. My H2SO4, H is 1.008, S is 32.06. Again, the table. So 1.008, sulfur is 32.06, and oxygen is 15.999. I have 2 hydrogens, I have 1 sulfur, and I have 4 oxygens. Now, I don't need any of those individual values, but that tends to be the way that I do this, just because sometimes I need them. This gives me 2.016, 32.06, and then 15.9 times 4, 63.996. And of course, if I add all of those lovely values together, that gives me 98.072. And that is grams per mole. That's my happy number that I need there. Now, I put that underneath the H2SO4. Do I need to do it for all the rest of them? Yeah, maybe, maybe not. But for me, just for me, because I want to make sure that I have whatever numbers I need, I tend to calculate all of that in the beginning. So I would calculate my NaOH, that's 22.990, plus the oxygen, which is 15.999, plus the 1.008 from hydrogen. That gives me 39.997, and I usually list this as grams per mole like that. My Na2SO4, I have 22.990 times 2, plus 32.06 from the sulfur, plus 4 times that 15.999 for the oxygen. It gives me 142.036 grams, and 1.008 times 2 plus 15.9 for the water is 18.015. Now, again, do I need all of those? No, I don't. I absolutely don't at this point. But I like to do that, again, systematic. For me, it's faster if I do them all at one time, because then that's where my head is. So there's that. Now, I need to convert from 500 grams of H2SO4 to moles. And so I take my 500 grams of H2SO4. I need to use a molecular weight to do that conversion. I want this in 1 mole, so I want answer of moles. So I'm going to divide by the 98.072 grams. That tells me how many moles that is. 500 divided by that 98.72. So if I were to report that at this point, that'd be 5.0, 5.10. Wait, 5.846 moles. Now, am I going to report that? Maybe. If they ask me how many it is, then I can report it. For me, I'm going to continue this calculation. because I want to go from moles of H2SO4 to give an answer in terms of sodium hydroxide. Now, this question is not specific about what units it's looking for my sodium hydroxide. It just says how much. So I can answer that in two different ways. One is in terms of the number of moles, because that is a how much, or I can do it in terms of grams of NaOH. Entirely up to you which one you decide to do. There is no specificity given here. So I can either report this in moles or grams. If I were going to do it in moles, I know that there's 1 mole, and actually, have I finished balancing this equation? Darn good question now, isn't it? And from looking at this, I can see that I have it. So I know that this had to be an Na2SO4 because of the charges. That means I have 2 NAs on my product side and only 1 on my reactant side. So that means I need 2 there. And of course, if I have 2 OHs here and 2 H's here, that means I've made 2 H2Os. So that changes things a little bit. And that's why I said we need to have a balanced equation. Now, should I have done that before? Absolutely. Did I recognize that I hadn't done it? Yeah, I did when I was looking at my equation. So is it imperative that it gets done at the beginning? No, really not. And actually, that's still 1 mole of H2SO4. 1 mole of H2SO4. Get rid of the moles there. Gives me 2 moles of NaOH required. So if I do that calculation, that tells me that I need 10.1, if I want 4 sig figs, it's 10.196, which I would round to 10.20. And of course, since it's 4 significant digits, I need it to be that 2 zeros and not just 2. So yay, I can report it that way. But I could also take and calculate this to the number of grams. And the way that I would do that is to multiply by that mass of NaOH. So I would take that 39.997 grams per mole. And that would give me the mass of that material that I actually needed. And that gives me 407.8 grams of NaOH that are required. Cool. Awesome possum. Questions about that? Okay. I'm going to take and look at the second one. Nitrogen trichloride reacts with water to form ammonia and hypochlorous acid. Nitrogen trichloride is going to be an NCl3, reacts with H2O. That's going to give me ammonia and H3 and hypochlorous acid. Oh, okay. Where do I find hypochlorous acid? Well, the first place I'm going to look is in my strong acids list, and I don't see it there. So then I say, all right, well, is there other information? Maybe, maybe not. So I might be able to ask my teacher. I might be able to look on the last page of this, and what you'll find is that it's not there. So how do I know what hypochlorous acid is? I would have to Google it at this point. But I know it's HClO. But that would be the way that we would do that. So there are a number of places on the test that you could look to see if it was there. So there, on page 6, there's a list of strong acids, strong bases. So it might be there. There's also a list of weak acids that's on the last page of the handouts. And it might be in there. But you also might find it in the last thing, which is diprotic acids and polyprotic acids. So it might be in that list as well. And it's not in any of those. So there you go. That's why I had to Google it, but it's HClO. Okay. So questions about that? And yes, I do everything I can to make sure that if it's not in the handouts, that you're given that formula on the test. Okay. So at this point, I see there's 1 nitrogen on my reactant side and 1 on my product side. I have 3 chlorines here, but I only have 1 there, so I'm going to multiply this by 3. That then tells me that my nitrogens are good, my chlorines are good. I now have 6 hydrogens on this side and only 2 on this side. So I'm going to multiply this by 3. And of course, that gives me my 3 oxygens there and 3 oxygens there. So awesome. That's balanced. Love it when that happens. I have 125 grams of nitrogen trichloride, and I need to know how much ammonia is produced. So I want to know about this one. And I know that I start with 125 grams here. Okay. Nitrogen trichloride. So my nitrogen from my periodic table, somewhere I have one, I do. Nitrogen is 14.007. 3 times my chlorine, which is 35.45. That gives me, this one is 120.35. And just because there's no space, I'm going to go ahead and just do the ones that I need. I know the other one I'm looking for is an NH3. So that's, again, 14.007 plus 3 times that 1.008 hydrogen. Again, it's 1.008 from there. So that's going to give me 17.031. And again, the only reason I'm not doing all of them is because, 1, don't need it, and because I don't have a ton of space. So that's why I'm not doing it. But since those are the 2 that I'm looking for, then I'm okay with that. All right. So if I'm starting with that 125 grams of NCl3, let's see if I can find some space here. I can take that 125 grams of NCl3. I can divide that by the 120.359 that I calculated, grams per mole. And that will give me moles of NCl3. I can take that answer and then multiply that by 1 mole of NH3 is produced from 1 mole of NCl3. Now again, I said, do I always need this? No. Am I always going to write it? Yes. For me, I do. Because if I look at a calculation that I've done and that molar ratio is not present, I know that there's a place that I could have made a mistake. If I have included that molar ratio, I know that I checked it and it's a 1-to-1, so it didn't matter, but I know that I checked it. So that's why it's important to me to include it there. Once I have that, I can either leave this, and again, how much ammonia is not specific as to whether it's grams or moles. So I can leave that calculation at that point, and I take my 125, I divide that by the 0.359, and that would give me 1.038, and it's actually 1.04 moles of NH3. Or I can continue and multiply that by the number of grams per mole. Moles cancel there, grams cancel there, so that leaves me with grams of NH3. So I can multiply that by the 17.031. And that would give me 17.7 grams of NH3 that are produced from that reaction. Okay, so again, I can do this grams to moles to moles to grams, or grams to moles, depending on how I want to handle it. Questions about that one? All right, now I am running out of space, so I hope that you still have the slides available for you to look at. I'm going to go ahead and go to a place where I have a little more space to write, because this is driving me insane, which I am insane, so that doesn't surprise me very much. note page, and we'll talk about the next one. So the next one states oxygen reacts with propane. To yield carbon dioxide and water. And it says if 25 grams of propane are used, how much carbon dioxide is formed? Okay. Oxygen, again, O2. Propane. Propane is a common name. It is it actually? I don't think it is listed again. When I was doing this one, I hadn't made these handouts yet, so not here. Propane is C3H8. It's one of the compounds that we talked about earlier. That gives me CO2 plus H2O. Now we balanced this earlier. So I had 3 carbons here. I need 3 there. That then gives me 6 oxygens, but I also have the 1 here. I need to have 8 hydrogens. So I'm going to multiply this by 4. That's what we did last time. That gives me my 8 hydrogens on both sides. I now have 4 plus the 6 is 10 oxygens on my product side, which means that I need 5 oxygens to make that work. Okay. So that's my balancing on that. My oxygen, the mass on the O2, 15.999 times 2 is 31.998. And I'm starting with 25.0 grams of this. I want to know how much propane I'm going to need. So my mass of my propane is going to be 12.011, the carbon, times 3, plus 8 times the 1.008 for the hydrogen. That gives me 44.097. Start with what I have. What I've been given, 25 grams of O2. I want to convert from grams to moles, so I use the molecular weight to do that. 31.998 grams of O2 per mole of O2. I know that I have 5 moles of O2 required to produce 1 mole of C. No, I don't want 1 mole of C. I was looking at the propane, it's not the one I want. 3 moles of CO2. So I could report this as the number of moles that I produce. Again, nothing specified about what unit it needs to be. Or I could set this up to grams of O2, 3 moles of CO2, 5 moles of O2, and then 1 mole of CO2 is 44.097 grams. Now, this calculation would give me mass in grams. So if I do the mole calculation, 25.0 divided by 31.98 times 3 divided by 5 gives me 0.46, and it's 9 moles of O2, because again, I have to round that up to give me 3 sig figs. I can also take and calculate the weight by multiplying this by 0.44.097, and that gives me 20.7 grams of CO2. And notice I didn't put grams of CO2 there, and you may see that I'm a little neurotic and I tend to include what that species is. And that's because if I have moles here and grams here and moles here and grams here, it can be very easy for me to confuse which one is which in terms of grams and moles and everything else. So I like to include the entire title. It's moles of O2, grams of O2, because then I have less confusion for me when I'm looking at it. Is that required? Absolutely not. If I were to see this as 25 grams divided by 31.998 grams times 3 moles divided by 5 moles times 44.097 grams per mole, that would be fine. Okay. What I won't accept, and I will not accept it, is 25.0, 31.998 45 44.197. And why won't I accept that? Because there are no units. So while I may be able to follow that that is the calculation you should have done, the problem becomes, if you didn't do that calculation correctly, how am I supposed to give you partial credit for that when I have no idea that you know what those numbers are for? So I can't give you partial credit if I don't know that you know what those things are. The only way I know that you know what they are is if they're labeled with units. Okay. Now, again, I don't need to know that it's grams of this or grams of that. That I can grasp from context, but I need to make sure that you've given units for them. The other thing is that we need to make sure that we've canceled those units appropriately. And I cannot emphasize to you enough, there is an example in your textbook of a calculation that was done here in the US, which was then provided to people in the UK to do some additional work with. There were no units with that number. And so an assumption was made about what those units were, and that assumption was very wrong. And so all of the calculations that came after that transfer were wrong. That meant that the space station that was built was completely not correct, and therefore unable to make the measurements that it was supposed to make. It couldn't observe what it was supposed to observe because it was made incorrectly. That's a really expensive mistake to make. So units matter. We need to make sure that they're there. Okay? So I've preached about my units again. I apologize. I'll come down off my soapbox now. So that's how I would set that one. Questions about that? Okay. My next one says that carbon disulfide reacts with oxygen to produce carbon dioxide and sulfur. Using 152 grams of carbon disulfide produces how much sulfur dioxide? So 152 grams here. I want to know how much sulfur dioxide I've made. So carbon disulfide, C for carbon, sulfur is S. There are two of them, CS2. Reacts with oxygen, which is an O2, to produce carbon dioxide, CO2, plus sulfur dioxide, SO2. Okay. Now, one carbon, two sulfurs, one sulfur. So I'm going to multiply that by 2 to fix my sulfur issue. I now have 2 and 4. That's 6 total oxygens. So I'm going to multiply that by 3 to give me the correct number of oxygens that I need. And I know that I'm starting with 152 grams of this, and I want to know how much of this I'm going to make. My mass for my carbon disulfide, 12.011 for the carbon, plus 2 times the sulfur, which is 32.06. This mass, 76.131 grams per mole. And my carbon dioxide, again, is 12.11 plus 15.999 times 2, which is 44.009. Okay. All right. Oh, I actually want to make sulfur dioxide, carbon dioxide. oops, I put my question mark in the wrong place. So SO2 is the mass sign. 32.06 plus 15.99 is 264. And that was not intentional, but that is one of the reasons that I always calculate all of them first, just because I need to make sure that, it's one of those things where either I might have written it down wrong, might have made a mistake when I was doing something and I actually needed a different mass, or they may ask me about something else later. And we'll get to that part when we talk about limiting reagents, and you may need all of those masses to be able to finish this. So for me, it's just easier to do all of those calculations at one time. So, all right, I want to go from grams of carbon disulfide, CS2, to moles of CS2, to moles of CS2, to moles of SO2, and I can either stop it there or go to grams of SO2. So one of those two. Let's set up the beginning of this. 152 grams of C2. That's how much I was given. I know its molecular weight is 76.131 grams of CS2, and that's per mole of CS2. Now in moles of CS2, I have 1 mole of CS2 to produce 2 moles of SO2. So now in moles of SO2. And so I can stop there, or I can take and continue this. Equal sign yet. I need to multiply by the molecular weight, which is 64.058 grams of SO2 per mole of SO2. And so I get my grams of CS2, the moles of CS2, the moles of SO2 to give me grams of SO2. So those are calculations that I can do for this. 152 grams by 76.131 grams per mole times 2 divided by 1. I don't actually explicitly need to do the divided by 1, but I did. 3.99 moles of SO2. I can multiply that by 64.058 grams per mole, and that gives me 256 grams of SO2 that are produced. So those are all of my calculations, and I've done them over and over and over and over again. I hope that you can see that for me, I try to set them up the exact same way. Write my equation, balance the equation, write the information I'm given above the equation, use the molecular weights below the equation. That way all of my information is in places that I expect it, and therefore I know what to do with it. I try to make that systematic so that way it's always there when I need it. I know exactly where it's going to be. It just makes my life easier. Is it necessary? No, absolutely not. Questions, comments, problems about the calculations we've done so far? All right. Are we done yet? No, of course not. That would be too easy. We're not quite done yet. So what else are we going to be talking about? Well, I said that there were other topics. Stoichiometry was the first of them. Limiting reagent is the next. So remember back before when I said that we were going to assume that there was enough nitrogen to make this work? Well, now we're going to talk about what happens when that's not the case. So the way that in my head this worked, I didn't always understand why I needed to be concerned about both of them. Well, let's think about this from a practical standpoint. I like to make hot dogs. My husband's a burger guy, great, but I like to make hot dogs. And so my kid likes hot dog buns. I don't, but okay, fine. If we go to the store and we buy hot dogs and buns come in packages of 8. Hot dogs either come in packages of 5 or 10. It depends on which kind you're buying. Now, why is that the case? And here's the real answer. It's because you make more money that way. So in my head, there's a conspiracy between the hot dog bun people and the hot dog people trying to make more money. That's probably not why, but I don't really understand the practicality of why they're done the way that they are. But if I want to make sure that every hot dog has a bun, the only way that I can make that happen is to buy 5 packages of buns and 4 packages of hot dogs for the ratio that I've been given here. Right. But what if I don't have that? What if I only buy 1 package of hot dogs? Well, if I only buy 1 package of hot dogs, then I only get 5 hot dogs that have buns. If I only buy if I buy 2 packages of hot dogs, I can only get 8 hot dogs with buns because I only have 8 buns. So unless I change that ratio and buy 2 sets of buns, then I don't have hot dogs with buns. Okay. And so what we see here is that I'm limited by how many hot dogs that I have in that first case. In the second case, I'm limited by the number of buns that I have. This is what we mean by limiting reagent. So if I don't have enough of one of them, that determines how much I could make. And that's what we're talking about when we talk about limiting reagents. So there's a factor that limits the finished products that you can make. Limiting reagents are the exact same idea. Okay. So let's consider the reaction that we talked about before. 3H2 plus N2 goes to 2NH3. And we had 16 grams of H2. Now, that's the calculation that we did previously. What if we have 16 grams of N2? Let's just say that we have the exact same amount of N2 present. Okay, that's awesome. Well, we made 90 grams of NH3 when we had 16 grams of H2. But if I set up that calculation in the exact same way, so I have grams of N2 divided by the mass of N2 per mole, I then have moles of N2, and there's 1 mole of N2 per 2 moles of NH3, and then in moles of NH3, I have moles of NH3. 1 mole of NH3 is 17.031 grams of NH3. I can only make 19.5 grams of NH3. That's a big difference. Okay, and so we have to consider that. So there are 2 factors that are involved in this. One is the ratio between the 2 of them. The other one is the molecular weights. It's complicated to do that math, like guesswork in your head. So the only way you'll know for sure which one is the limiting reagent is to do the calculation. Now, you may get asked, what is the limiting reagent here? And you could absolutely guess this one or that one. H2N2, H2N2. Here's what I'm going to tell you. Even if you guess correctly, unless there is a calculation that shows me why you guessed that, I am not going to give you points for it. Because guessing 1 out of 2 is not really that informative. Okay? I need to know how you know that. And so the logic for that is these calculations. Okay? So that's what we're going to be looking at. Now, why am I saying that as well? There's no way to predict from a balanced equation which material will be limiting. It's just not possible. All right. So the number that you calculate is what we call a theoretical yield. And I mentioned this because I mentioned before that not everything is 100% efficient. And that's right. So this number that I've calculated, based on my limiting reagent was 19.5 grams of NH3 that I should be able to make. Am I actually going to make that 19.5 grams? That depends. And it depends on a lot of things. So that's what we call a theoretical yield. We'll come back to yields in just a few minutes, but that's what we're talking about in terms of yield. Right? Now, let's talk about our limiting reagent calculations before we get into yields. Oh, no, I'm actually going to do it this way. Okay, fine, never mind. So what I actually produce is called an actual yield. So I have a production, I do this actual thing, and I make some amount. Almost all reactions are reversible, so not all material is going to be converted to product. This is something we don't really talk about in this class, but that's definitely true. Products can react further to produce other materials. That changes the actual yield of the product that we're looking for. Recovery of that product may be difficult, so you may end up with losses from that. So our actual yield is never the same as our theoretical. There is no process that is 100% efficient. It never is. So chemists will want to know how efficient that process is. We determine that by calculating a percent yield. My percent yield is the actual yield divided by the theoretical yield times 100. Now, I mention this also because ammonia, this thing that we've been talking about, is difficult to produce. The industrial process, which actually has a name, it's called the Haber process, is only 28 to 29% yield. Okay, that's important because if I actually need to make some specific amount of ammonia for some order that I'm doing, I need to know about that yield percentage to be able to figure out how much I need to start with to make that amount. Okay, so this is why that's important. Now, what can we do with all of that? Well, there's a number of things that we can do with that. And one of the things that you can do, and what I'd like you to do now that we're done talking, is to come back to look at these calculations that we've done previously. Our example calculations, we gave a mass for this material, right? So it was for one material. I want you to assume that you have the same mass of the other material and calculate how much product you can make from the other material. Okay? So same mass of other material. Right? Then, once you've done that, I want you to look at how much would you actually get if your yield was 50%. So if I had a 50% yield, my actual yield is half of my theoretical yield. Then how much material would I be looking at to make that work? So how much actual yield would I get? So you've calculated this theoretical yield. That's what you've calculated in these calculations. What would your actual yield be for each of these cases? Now, do we normally do it in that way? Yeah, sometimes not. It depends. All right. But that is something that we can do. Now, that's what I'm going to be doing for the rest of the time that I'm hanging out here, is walking through those calculations. So what would it look like if I had 500 grams of sodium sulfate rather than 500 grams of sulfuric acid? How much product would it actually make? And then tell me, what is your limiting reagent? And of course, my limiting reagent, with the example that we talked about with the NH3, would be the second one that I talked about. And if I'm not mistaken, that was the nitrogen that was my second. Should be. Yeah. So when we talked about the nitrogen, I ended up with a smaller amount of product. So my nitrogen is my limiting reagent because of that smaller amount of product. So I would identify N2 as my limiting reagent. So that's what I want you to do. What is the theoretical yield from both of them? Which one is the limiting reagent? And then what will your actual yield be if your percent yield was 50%? That's what I want you to calculate. And I will throw those calculations up if people don't want to hang out. I will throw those up on D2L if you're interested in looking at them. And it's perfectly fine. Like I said, I'm going to continue walking through these calculations just so we can see what those will look like. But that's what we're going to be covering for this. And that takes us through the end of the materials for the first test. So do I have any questions, comments, problems, concerns, anything from anybody? Okay. Then I'm going to go back and start doing some additional calculations. So like I said, the last time I did this for sulfuric acid. So now I'm going to assume that I have 500 grams of the sodium sulfate as well. Mass for my sodium sulfate, which I didn't calculate before. Oh, actually I did. It's right here. 142.036 grams. All right. So I take 500.0 grams of Na2SO4. I divide that by the molecular weight, 142.036 grams of Na2SO4 per mole. Na2SO4. I know that the relationship there's 1 mole. No, I don't want to do it for sodium sulfate. No, that's my product. I want to do it for sodium hydroxide. Oops. I have a reagent. So 39.7 grams of NaOH. Of NaOH. There are 2 moles of NaOH required to make 1 mole of Na2SO4. And again, I can cut this off at the mole level, right? If I do that, I calculate that I have 500 divided by 39.997 divided by 2. That gives me 6.25 moles. And I calculated previously that I would have 10.20 moles of NaOH that were required to do this. What that tells me, because I'm comparing NaOH at this point, is that I don't have enough of that 39 point, that mass of 500 grams of NaOH is not enough to use all of the H2SO4 that I have present. So H2SO4 is present in excess. NaOH, based on that 500 grams, would be my limiting reagent. And I can say that because of that mass calculation, or the moles calculation that I've done there. So do I have to take it all the way to grams? No, I don't. Absolutely, I don't. But there is a way for me to do it at the mole level. Okay. Yes. Questions, comments, problems? Okay. So my limiting reagent is my NaOH. And of course, if I wanted to look at actual production of product, so I can take that 6.25, I can calculate the amount of product that I'm going to make from that by using the 142.036. That tells me that I would be making 887.0.8 grams of Na2SO4 that would be produced there. 50% yield means I'm either looking at 6.25 moles divided by 2, so 3.125 moles that I'm making at 50% yield. Or I can take that 887 divided by 2, and that gives me 443. It's important. Grams of Na2SO4 that would be produced at 50%. Okay. So again, I can look at how do I find which is my limiting reagent? How do I find how much I would make at that 50% yield? If we look at our second one, our nitrogen trichloride reacts with water to form ammonia and hypochlorous acid. 125 grams of nitrogen trichloride is used. How much ammonia is produced? So we looked at from the 125 grams of NCl3, what if we did it with 125 grams of H2O? I calculated the mass for the H2O right here. So I can use that. And I can take that 125 grams of H2O. I can divide that by the 18.15015 grams of H2O, a mole of H2O. I know that there's 1 mole of H2O that are in, that's actually 3 moles of H2O. And I produce 1 mole of NH3. That number of moles is then 2.31 moles of NH3 that are produced. When I did this previously, where did I do? Oh, I didn't actually calculate it. So, gee, if I had cut it there, I could have done it. But I can multiply by the 17.031 grams, which I did previously. Oh, I did do it. Sorry, my moles was over here. 39.39 grams. And in either case, I see that I make 2.31 moles of NH3 here, but I only made 1.04 moles of NH3 previously. So the NCl3 is my limiting reagent there. Okay. Awesome. I figured that out. When I come and look at the other two calculations that I've done, I have 25 grams of O2. I can react that with 25 grams of the propane, or that I'm struggling to find. And if I look at my propane, if I do 25.0 grams of C3H8, divide that by the mass of the C3H8, 12.011 times 3 plus 8 times 1.008, because I think I calculated it, 44.097. 1.91 plus 20 times 15. Ah, hooray. So this mass that I calculated here doesn't actually go with that. It goes here. The CO2 is 60.008. Meaning my calculation here is wrong. The number of moles is correct, but the mass is incorrect. C2. So dividing by my 44.097 grams of C3H8 per mole, C3H8. I can then bring that answer down. I know that 1 mole C3H8 produces 3 moles of CO2. So I can cut that off. Yes. There. Or I can multiply by the mass, again, 60.008 grams per mole. So 25.0 divided by the 44.7 times 3, 1.70 mole of CO2. And of course, based on the mole calculation we looked at previously, I know that my limiting reagent is the O2 because I had 0.469, not the 1.07. So I know that that's my limiting reagent is my CO2. Okay, I can go ahead and do the mass calculation. 60.008, just to figure out what that mass would be. 2, and that is grams of CO2 that are produced. If this is a 50% yield, then I'm looking at 0.469 moles divided by 2, so 2, 3, 5. So CO2 are actually produced, or I'm looking at 28.1 divided by 2. So 14.5 grams of CO2, and that's from the production with O2. Okay, cool. So now I can look at my my last reaction, CS2 plus 3O2 versus CO2 plus 2SO2. Again, we are going to assume that we have 152 grams of the O2. So I have 152 grams of O2, 1 mole of O2, and that's 31.98 grams of O2 per mole. I have 3 moles of O2 required to make, looked at production of SO2, so 2 moles of SO2. That'll tell me the number of moles of SO2 I produced from there. 152 divided 31.98 times 2 to 3 gives me 3.17 moles of SO2. And they're not distinctly different, but that is definitely different. So my O2 is my limiting reagent. If I multiply that by the mass of SO2, oh, my erase, it doesn't actually work. 8 grams, 2 moles of SO2, 3 moles of O2 are required, grams cancel for grams, moles of SO2. 1 mole of SO2 is 64.058 grams of SO2. Sorry, calculator issues. It happens. 202 grams of SO2. So again, that is what we're looking at there. So that's the mass that I actually could produce. Since I'm looking at 50% yield, I divide that by 2. That tells me that I would actually produce 101 grams of SO2, or 3.17 divided by 2, 1.59 moles of SO2. And again, that's my limiting reagent, so that determines what it is, and that came from 2. Okay, so there's that. So that's everything I was planning on running through today. Again, does anybody have any questions, comments, problems, any concerns? All right, then I shall be hanging out, ready to answer any questions anybody may have.
In regards to practicing yield, actual, and figurative, and anything else, I'm sure there's some work in Alex that's for it. Is there any additional practice work that you might be able to suggest?
Yes, so let me grab my here. So additional practice work. There's a number of different types of practice work that are available. Alex has one. There is some lab stuff, so you'll probably see percent yield in some of the labs that we're going to be working with a little bit later on. It's not that soon, but you'll definitely see it there. There is in our content, if we go into our stoichiometry, some of the practice that is in here will have yields that goes with it. You'll see percent yield calculation right here. There's one there. So there's a couple of things that you'll see in there. The other thing that you'll find is if you come to the in-class practice sheets for stoichiometry, you'll probably find some in here. And if that is not enough, I am more than willing to find you more.
All right, thank you.
Sure, no problem. Anything else?
Where are the recorded lectures in the content section? So like under stoichiometry, under
Yes,
chemical reactions, so on and so forth.
Chemical reactions one is right here. You'll see a web link for that. The stoichiometry one will go up later today, and it will also be a web link under stoichiometry. Yep.
All right, awesome. That's all I got for today. Thank you so much. Have a lovely day.
Thanks. Have a good weekend.
Um, are you still available today? If I'm able to
Um,
come in.
I am available until 10, and then I have to leave. I have some
Okay.
volunteer work I do today.
Okay. No worries.
But I can meet with you this weekend if you want.
The weekend, Sunday work, maybe?
What
Or,
time?
I'd say morning.
Okay. What time in the morning?
I mean, it doesn't matter. 9
Um,
or 8?
well, okay. Eight would actually be fine. Yeah, I can do
Okay.
that. Because I
Okay,
have
let's
a thing I do at 10, so I can definitely do 8. That's fine.
okay.
Awesome.
Yep.
I will
I just wanted to go over a bunch of Alex stuff
okay.
because
And we can do that via WebEx. You can share your screen to me and we can do it
right.
that way. Yeah.
Okay. Yeah,
And
'cause
I'll
like it's
go ahead.
getting confusing. Like the one that you taught me like in person was easier, and then when I hop in Alec, it's just like, what am I doing? Like I don't know, you
Sure,
know. So
sure.
yeah.
And I understand. I understand. It's not a big deal. I will send you a reminder through D2L that we're going to meet on Sunday at 8. It'll have a link in it so that you can meet me up on WebEx, and I'll see you at 8 on Sunday.
All right. Thanks.
You're welcome. Have a great weekend.
You do the same.
Thanks.